Now discuss about GPUs. So, the GPU information, this technology is rapidly changing. There are books on GPU, but you will not find the information on any book in well, GPU is not contained in any recent book. This processor GPU which is recently released is only 1 year old. So, you need to go to the website and look at the, you just need to search. So, the companies, the NVIDIA, AMD, Intel, they have some details in their website. Okay. NVIDIA has maximum detail, NVIDIA is reasonably, it is also there is outreach, they want to reach people. AMD is not so good right now on that front. So, some of this material I have listed here, you can click and you can read more about them. So, GPUs were basically for graphics, right. So, by name itself graphic processor unit. So, earlier there used to be, in fact, you have seen this picture in my presentation in my class. So, the CPU and the GPU was in the side. So, CPU was doing most of the work, but for graphic stuff like rendering or image, the too big a image and the CPU is not able to handle it, or CPU says, well, I need some help. So, GPU used to do that rendering or video editing that was done before. Well, it still is being done now, okay, and I can't say before. The movie makers or the animation guys or the gamers, actually, that so gaming is, I am sure there are some of you who are gaming experts. So, gaming needs fast GPU. CPU does not, well, basically CPU will just give some commands. So, GPU do this. Okay. So, GPU is basically for graphics, but then this companies realized NVIDIA first, saying that I can use the GPU for HPC, for numerical simulations as well, because we have lot of computing units inside, 5000, okay, that is the number approximately. So, if you compute, then it will be can be quite fast compared to CPU. So, that idea caught on roughly around 2005, 2006, okay. That is where this GPUs which were used for graphics, in fact, you can use the same GPU for computing. Every laptop has a GPU. So, some of the codes, if you have NVIDIA GPU, I do not know, some RX 4090, RX 3090. So, you need to see which is NVIDIA machine, then your CUDA code which we will develop right now in our in our course can run on your laptop, it is the same GPU. Okay, there is only one, so NVIDIA had two series, this is called Quadro series, which is for only graphics, and other one is for computing series. So, the difference was, well, in the beginning, okay, let me just make this clear, out of 5000 odd cores, GPU cores, some cores may not work or some cores may not be precise, some errors may be there. If somebody asked me what is some error is there. So, if some core is not perfect, still your gaming is not affected, as long as the computer program does not crash, and these codes will not crash, one pixel will be faint. So, gaming is not affected by imperfection of any of the, if failure of few codes, but your HPC program will fail, right. I have some simulation, critical simulation, some error at some data point can have strong effect on the future output. Like weather, I mean, if I make an error in some weather station, some wrong input is put, the weather prediction will be very different. So, for this one they said, well, we will wait for a while and release same cards as a HPC cards. So, that is only difference. It is the same card, they have no different design for HPC, it is the same card which is used. Okay. The HPC cards are bit more expensive, because okay, I mean but it is basically the same card. There are some other games which is being played, which we can discuss later. So, this is the Quadro for graphics and Radeon for AMD. So, AMD is a big player. Intel had their own GPUs, okay, that was attached with CPU. And Apple has its own GPU sitting there for basically it makes rendering fast. The people who work on video editing of our videos, they need GPUs. Okay, but now let us do HPC with the GPUs. So, I will discuss only the latest GPUs. So, there are series, you can just go to Wikipedia and look at lot of starting from 2004, 2005, what are the GPUs. So, the latest is H100, okay, H for Hopper architecture. I think they are running out of names, you know. So, Ampere, so Ampere we know, right, physicist Ampere. So, this is A for Ampere, H for Hopper and V for Volta. So, this is a series 100, and now if they put more cores and they call it 200, they put more cores and call 300. So, that is a series. So, A100 is something like 3 times faster than V100 and H100 is roughly similar 3 times faster. So, it depends on which application, but we will discuss some details after today right now. So, this is a V100 inside the card and this is H100. So, there are two things sitting here, this is one and this two. So, this is a GPU, I can't figure out really the difference. So, one of them is GPU, other one is CPU. So, NVIDIA has its own CPU now. Well, I am not very we do not have it, but it. So, Intel or AMD CPU and GPU of NVIDIA. So, in our machine, like there is a Intel processor and a GPU of NVIDIA. That was used to be the trend, but now NVIDIA thinks that they can give optimized hardware with their own CPU. Okay, so, that is their CPU is called Grace CPU, that is a name given. So, I think it is either released or to be released. So, how does a GPU look inside? So, this is what I think you should pay attention to this. It is a very different architecture than a CPU. This is a schematic. Okay. So, CPU we discussed like ROM processor, no CPU. Now, CPU is connected with RAM, also this one is GPU. So, the GPU, RAM and CPU. Okay. Now, GPU has many computing units. So, SM, some of these names come they are basically coming from graphic nomenclature. So, streaming multiprocessor. So, stream graphics. No? So, SM is streaming graphic multiprocessor, and this one you can see that 12 of them. Okay. And each SM, so this SM is expanded, this one is expanded into, you can go inside. It has SP is scalar processor, there is a cache, data cache, instruction unit and shared memory. So, each of this SM has its own memory and cache, okay, and registers. Okay. So, you are packing lot of computing units. SP is the computing unit, this one is a computing unit, and there is a lot of data sharing. Okay. So, the data is shared among all this SPs. So, basically the data is residing inside the GPU, and we are not, basically the speed comes because in typical CPU we have data sitting in cache, but most often you have to go to RAM, right. You basically keep going to RAM. Here memory is very close to the computing units and they are shared. So, cache miss is very unlikely for GPU, there is no cache miss, you keep all the data inside, then only start working. But this requires very specific kind of applications. It should be vectorized, the data should sit inside. I am not going to look for data, if you do not give me the data now, I will not work for you. So, that kind of architecture is here. CPU can say, well, the data is not there, I will get it later, no problem. So, this is basically vector operations and data is sitting inside. So, there are very different strategies for execution. So, this is A100. Now, yeah, I am sure you can't see what they are. So, these are the SMs, okay, there are 128 SMs sitting inside, and this is L2 cache, and remember every SM has its own cache and RAM. Okay. So, and the RAM from which data will flow to cache, L2 cache and L1 cache are in the side here. Okay. And these connections are also very fast. These are interconnect which we will discuss, these are very fast connections. Okay. So, this is a A100 GPU. So, let us look at some strategies of GPU. So, it is SIMD, single instruction multiple data, we discussed that before. So, like matrix array by array multiplication. So, C equal to A star B. So, I mean to multiply AI with BI, right, that is what. So, this is not a matrix multiplication, okay, or actually A could be a one dimensional array or could be 4 dimensional array. Every element of A is multiplied by respective element of B and result is put in same index for C. Okay. So, it is called element by element multiplication. So, instruction is multiply elements and you can put 1000 elements in one shot. Okay. So, single instruction is multiply, whatever data you give me I will multiply, and multiple data. Okay. So, this is called SIMD which is executed here. In CPU we have 16 of them maximum right now, but GPU has thousands, in fact it can literally work with 5000 number in single shot. So, single instruction multiple threads, it can also spawn threads. So, we discuss threads, no? So, it can just say, well, same operation many of them will do simultaneously. So, these are the technical words. GPU runs a kernel. So, program is called kernel. Okay. So, when you run a job then it is called kernel. It is massively multi-threaded. So, threading is coming now, right, I mean you can see threading. So, this one will, so let us say we have 1 million numbers. So, it can generate 1 million threads, it can, the number of threads can be more than CPU, number of threads you do not do it, see the GPU will decide itself. Typically for a programmer, I mean good programmer can dictate it, but as a user, a scientific computing, you do not dictate how many threads you want to generate typically. Okay. You can, I am sure you can do it, but let the computer, you give the array size and it will generate threads, but you should know the idea what it is doing inside. So, you have massively multi-threaded, so it can do 1 million threads, and kernel is divided into thread blocks. So, I will show you a picture. So, the threads are not like thread, you understand, no, the thread for cloth, making cloth. So, there are hierarchy. So, there are thread blocks, then thread, in fact combination of thread block there is some name for it. Okay. So, there are hierarchy of these thread blocks, and thread blocks are automatically distributing among SPs, the processors SPs. All threads execute one common instruction, one instruction at a time, and each SP has a set of registers which are shared among threads allocated to SM. So, they are SM then the SP, you saw the picture before, the SM and SP, and each SM can be treated as a separate processor. Okay. It is computing unit, you can call it core if you like. So, this is another thing, streaming multiprocessor SM. So, A100 has 128 SMs, remember. So, this is SM, just to SM each of them, and within SM this is called SP. Each SM can work different codes. So, it is not that full GPU is running a single program, we run 10 programs on a GPU. So, one SM is doing maybe fluid simulation, one guy could be molecular dynamics, this could be aerodynamic simulation. So, it is possible in a GPU, and but SP in one streaming multiprocessor executes the same instruction at the same time, but work on different data. Okay. So, SP is doing same instruction on multiple data. Okay. So, this is a interesting picture. So, let us start from the top. So, this CUDA enabled GPU. So, CUDA kernel grid. So, these are kernels, they are different programs. Okay. It is each kernel grid has a CUDA thread block. So, there is a number of threads, each thread will do some computing, okay, and that will sit in SM. Okay. You this CUDA thread block will sit in SM, and then you well there are many threads, but each some the thread will go into CUDA core SP, and within SP there could be multiple computing units. So, you can see that it can do thousands of operations every cycle, and that is the advantage of this one. But the one flip side is it can't do very general operations, it can do what can be can basically done simultaneously, like rotation, multiplication, Fourier transforms. But if you ask it to do some kind of complex stuff like database management, which is not vectorizable, no, when so that it can't do it. Okay. Now, this is other picture. So, it turns out presently the GPUs are mostly, well, there are HPC users, but who are the even more, there is a community which is using GPU much more than us.
Streaming and video editors.
Okay, they may be same as HPC right now, but artificial intelligence, okay, AI and machine learning, it is basically GPU intensive. So, NVIDIA basically is selling lot of GPUs to Google, all this AI, car industries, who are using AI, they are using GPUs. In fact, if you are using AI, then you will see that Google has, you can do well for small jobs, you can run it for free on Google cloud. Okay. So, well, I mean this you can't see very well. I will show you in the next slide what kind of hardware is there inside. It is not only for floating point operations. Okay. So, let us look at it here. So, we have floating point CUDA cores. So, 64 FE32, this floating point 32 bit. These numbers will change 8192, so that can become 10,000, but you focus on this FE32, int 32, integer multiplication of 32 bit. Then we have that is floating point 64 bit, okay, and so there shared memory which is significantly high, 192 shared KB, and L2 cache is 40 MB. But so we have both floating point operator cores and an integer operation cores, they are separate cores. Inside the CPU they are general cores, I mean we do not have core for doing only integer operation and core for doing floating point operations. That is what it is, it is a general machine, but then it is not as fast. Okay. So, well, I mean the very crude analogy will be a batsman does batting well and bowler does bowling well. So, these are, they have separate architectures. Look at those stuff in next set of slides also. And one important point is that this is GPU, this is also GPU. So, how do I know it is GPU? There, these blocks are supposed to be computing cores, okay, and this is a CPU, it has only 4 cores in some sense. So, there is a very fast interconnect between GPU and GPU. This is called NVLink, NVIDIA link, and this has speed of 600 GB per second. Okay. Compare it with PCI 4, which is 31.5 GB. PCI 5 is 63, right? We discussed that one. So, this one is 10 times more than PCI 5 or 20 times more than PCI 4. So, this NVLink is also helping in speeding up the programs, and now this one also is speeded up. This connection is also speeded up, and what NVIDIA wants is to have its own CPU, so that all these connections can be optimized. So, everything if you own it, then you have all control, you can better the hardware. It also has its own switch. InfiniBand switch is bought by NVIDIA. No? So, whole company Mellanox is now with NVIDIA. So, they are basically a big player right now in hardware. Okay, so, let us look at some numbers. A100 is not the best processor, best GPU right now, but let us look at the numbers which I had the details before. So, it has 54 billion transistors, 6912 cores, 9.7 teraflop, double precision, DP is double precision. So, that is what A100 GPU can do. Compare it with ROM processor. What was the teraflop for ROM double precision? 2 teraflop. Okay. So, this is 5 times faster. Single precision is 19.5 teraflop, double basically of this. Then tensor performance, it is AI application, okay, tensor 125 teraflop. So, you can see the speed, okay, they are 6 times the single precision speed. So, it is a special hardware, I mean they have neural engine sitting inside. So, it is a 7 nanometer technology, 40 GB RAM. Now, the new A100 has 80 GB RAM, 1.6 terabytes per second, that is memory bandwidth, okay, and it takes 400 watts of power. V100, you can see the numbers are slightly lower, 7.8 teraflop, which is not bad, but okay. RAM is bit lower, I believe, is 32 GB RAM, 32 16 GB RAM. Okay. Now, look at H100, which is most recent. So, released 22nd March 2022, 1 year old. Okay. So, it's 4 nanometer technology. It has 80 billion transistors. Now, the thing you should see is 80 GB RAM, but now there is one H100 processor which has something like 160 GB RAM. Okay. So, it is the packing RAM which was not there in the past. By the way, having more RAM is important. No? Why is it important? More data you can fit in. So, earlier GPUs, when I was starting to work on HPC, so that time 6 GB RAM in a GPU, and GPU programming is not easy. Okay. So, we will see right now it is easy, but earlier you need to write in CUDA, that is a programming language, and CUDA is pretty clumsy way to write the code. So, we said no, we do not want to spend time on 6 GB RAM hardware. So, we did not do work on it, but now it is huge RAM. So, we can now use GPU effectively, and not only, I mean lot of people have moved there because it has more GPU now. Okay. Few numbers I like to show you, this like 256 KB per SM, which is a big cache, and 50 MB L2 cache. These are big numbers for cache. Okay. And the floating point operation is 25 teraflop compared to around 10 in A100. So, 2.5 times faster. And if you look at this floating point 16, which is 205 teraflop. So, if you can manage with 16 bit floating point operations, it is giving you 200 teraflop. Okay. 16 point we do not work with that, but it will be, I think the errors will be too much. But for AI applications we do not care. AI applications do not, in fact they also are happy with 8-bit operations. Okay. Like this image is a cat or a dog. The image, in fact every image has every pixel has 256 values maximum, right, 0 to 255. So, we can manage with 8 bits, okay, integer in fact, and power is 750 watt, okay, that is suggested power T. Now, compared to, so these are compared to A100, H100 is, so this is A100 relative to, so it is A50 is 6 times fast and this is called genome sequence is 7 times fast. Now, H100 also comes in various versions, right. So, you see there are different versions, and now I would like you to see this numbers. This is floating point we discussed, you know, the integer operation int 8, integer 8 bits, it is 8 so 7916 teraflop, that is 7.9 petaflop. Okay. So, our machine is only 1.3 petaflop in floating point. So, this is very fast for AI application. So, if you compare that with floating point 64, but this is very big, 134 is very significant. So, compared to that it is how many times fast? 80 times faster for AI application. Okay. And even like GPU is the RAM is 188 GB and the bandwidth is 7.8 terabytes per second. These are big numbers. Okay. So, programming, what do I use for GPU computing? So, CUDA is the best option. Well, I won't say best, you get the best performance if you use CUDA, okay, but it is pretty tedious. OpenCL is you have a C code, then you can use some something called Pragma, some commands at the top of the code, for loop function, and you can get to OpenCL. You can basically run the code on GPU, but it will not be as fast as what you get for CUDA. OpenHCC, there is another, these are similar. Okay. You basically write some commands to the compiler saying that okay, generate for GPU, and MPI compiler with Pragmas, that is one, and there is one more now which is coming is Python. You can use Python called CuPy. Okay, that is what we are using very much right now. So, you have Python code which is runs on CPU, the little change with very small changes we can run on GPU, but it will not be as fast as what you get for CUDA. So, we have a code which is compared to a single ROM processor, it is 3000 times fast, okay, compared to single core of ROM, but this is around 500 times fast. Okay. So, there is still speed difference of 6. I think we can make it better with maybe 1000 times, but there will be a difference between the two performance. Okay. So, let us look at AMD, and now we just discussed about NVIDIA, but AMD is also rapidly catching up, like number one machine is using AMD GPU. So, compared to A100, some claims we are not able to get it in our, we have this not this card, but we have 250. So, we have this card as well as AMI 200, sorry, AMI 200. So, if you look at the claim, let us look at floating point, it is claiming that you can get 43.1 teraflop with AMI 100 itself, and NVIDIA is getting 19.5. Okay. We are not getting that speed. Okay. This is, we are getting in fact less than A100. Maybe there is a problem in our program, but this is what is a, well, of course, some code will run at that speed, they cannot lie on, they will report number which is tested, but these numbers are, I mean, we need to tune your code, we are not able to get that performance. Okay. So, each of these operations are faster, 92 compared to 39. Now, this is various AMD GPUs. So, 256x what we saw in Frontier. Frontier uses 256x, it has 128 GB RAM and is a floating point 64. Where is floating 64? This is the one, 47.9 teraflop. Okay. But its integer, where is integer? Int 8 is 383 teraflop. So, int 8 is quite fast, and these are the numbers. We do not have 250, but we have MI 200, which is somewhere 200, not this. I think we have 210. Okay, MI 210. We have this one. Okay. So, GPU box. So, instead of one GPU unit, we can put many of them. Okay. Then it will be even faster, right? So, please keep in mind that there is a performance loss when you go from one GPU to the next GPU. Right? Why? Because you need to transmit data over a cable, and these cables are slower compared to what you do it for with RAM or with cache. So, please remember, okay, cache, then we have RAM, then we have external GPU to GPU or GPU to CPU, then hard disk. So, if you can do within a GPU, great, but some problems are more sometimes bigger, then you need more GPUs. So, we need to get a machine which has more GPUs. So, this is a DGX box A100, it has 8 GPUs in it. Okay. So, this 40 times 8 is 320, now we can come with 640 with 80 times 8. Okay. Now, this is the box, you can see there is NVIDIA A100, these are well, they are inside. Okay. This is a box, this is a big box, heavy box, and it has basically 2 ROM processors, dual ROM, and 8 GPUs. So, it is a very fast box. I mean, it can do many lot of things this box is capable of, and it has also has NVLink switch between GPUs. Okay. So, it is a very capable box. Now, this is not new now anymore, this is a old box. CDAC has these boxes, the CDAC machine is basically built out of this DGX box. So, if you have money, you can buy this box, it is around 2 crores each box. Okay. So, new box is DGX H100, okay, this is the latest box, well 1 year old, and it has H100 GPUs, okay, and its performance is 7 times more than the previous box, 7-8 times for floating point. Okay. So, anyway, these are the boxes. It has Intel Xeon Pentium processor. Okay. Now, next set of boxes NVIDIA is planning is with its own CPU, and this is a AMD box. Well, we do not have the box, I do not get the picture of the box, but this is their box with 4 GPUs. Okay. This we saw earlier for while discussing Frontier. Okay, I just want to make one more remark, since we discussed about special hardware. So, we will discuss one set of programming set of application called finite difference. You heard of finite difference, right? Most of you might have heard. So, you can compute derivatives by taking the 2 neighboring points and subtracting the number. So, Newton's formula, no, df by dx is f x plus delta x minus f x by delta x. But suppose I have a big grid and I want to take partial derivatives, okay, a 3D grid, and so along x direction, y direction, along z direction. So, I have big grid, well, it could be 3D box or even 4D box. Now, I can't fit it in single GPU or single processor, then I want to put 2 GPUs or 4 GPUs. Okay. We will discuss this in more detail, but I have few minutes, so I can just discuss. So, when I take the derivatives along x direction, this is x direction. So, I take 2 points, neighboring point, and subtract 2 points, subtract. When I come here, then the neighboring point is in the right, then I need data from the right, right. So, that is where I need to share the data, I need to communicate this data. So, this data has to be shared every time. So, right guy needs the left data, well this is a forward difference, but if I do central difference I need the left data as well. So, this P1 will need data from the P0 as well as P2, correct, obvious. It is a 3D box and I need it for a plane, this slab will be a plane. Now, do I need a general switch or can I manage with some design where I do not need a switch and I can do faster? Switch is useful or switch is better or not, it will be a obstacle. So, remember switch will go, wire will go from here, so they all go to switch and the switch will route it. Okay. So, there is a switching will take time, I mean there will be a latency, right, we heard the word latency and data transmission. So, I suggest we should do something different. I do not have a. So, I suggest that we connect these wires directly between these processors, between these nodes. So, connect 2 wires each, this, and you can make a torus by connecting wires between this. So, each node has 2 left wire, 2 right wires. Okay. Or actually you can manage with 1 wire itself from left, 1 in the right. Okay. So, I want to send data, I should send right away from RAM here to RAM there. Do not go by any copy or any switch, just copy. We need to write a code which will send data to the next guy. Okay. So, this is, so the MPI does it for you in the background, but we can write a code which will take the data and put in the RAM there. I know the RAM address, I can just copy it. So, which will be faster, this blue operation or this going via switch? Blue operation will be faster, and this is a special design for finite difference machine. Okay. And right now we have very fast switch, not switch, fast cards like Ethernet card, which is not expensive, and you have fiber cables, it can send data very fast there. So, you can minimize the computing the transmission time, data transmission time. So, I think this kind of hardware is definitely will be cheaper and better. So, but somebody should take it up, and so general purpose machines lack this kind of innovation. So, one application called fast Fourier transform, which we will discuss it in this course, it requires communication between any to any. Okay. There are n processors, then I need to do FFT with n processors, then it will require n into n minus 1 by 2, that many connections optimally, but that will be for single hop, but typically we do not have that facility. So, we will have switch, it will go via switch, and that is a problem. Communication is slow, and that too you are not going in a single hop. So, there was a machine called Earth Simulator, 2003 I think, built in Japan, that had basically very fast processors and it was connecting every to every. So, switch was special design switch, and that had a FFT efficiency of around 50%. So, peak performance, it compared to that it could get 50%, the performance is 50% of the peak performance. Okay. The best right now, the best machines offer us around 2% or 1%, because you are going via switch and there is a we can't get directly there are hops, and until all the data is there at the right place, everybody is waiting. Okay. So, special machines are, they have their own importance, but it requires special funding and engineers to work on it. Okay. So, that general machines are okay, all people use it in institute, you can do chemistry, you can do physics with that. So, that is a trade off. So, Cray was thinking on this kind of innovation. So, you can innovate so that you can speed up some operations or some applications.